The universe's final moment is not a sudden explosion. It is a drawn-out execution, and it is worse than human time can meaningfully describe. Imagine drifting alone between galaxies. No sun, no Milky Way, just a thin frost of stray stars in an otherwise perfect black. For a while, it is peaceful. The last lights of the cosmos, scattered like embers on an ocean of night. Then you realize, there will come a time when even these embers go out. And physics already has a timetable for their deaths. This is the story of how scientists think the universe actually ends, step by step, across unimaginable spans of time. And why the final step may be the strangest thing the human mind has ever tried to picture. Number 1 is the moment when reality itself may stop working the way it does now. I've gone through the latest cosmology, from dark energy surveys to black hole thermodynamics. What follows is the best map we have of the road to the end. Let's begin. Number 7. The end of star making in 1997. A team led by Harold Maddow, publishing in the Astrophysical Journal, reconstructed the cosmic star formation history. And found something chilling. The universe's era of making new stars peaked about 10 billion years ago and has been collapsing ever since. On human scales, that sounds abstract. But imagine the Milky Way as a city where new lights used to turn on every night. Now, construction has stalled. Gas is used up or blown away. Fewer newborn stars. More dark windows. Extrapolating those curves, by roughly 100 trillion years from now, almost all the cold gas in galaxies will be gone. Star birth falls effectively to zero. What remains are long-lived red dwarfs slowly burning through their fuel in an ever-emptier sky. We have not yet watched a galaxy age all the way to that future. We have also never seen any known mechanism that can reverse the decline. Number 6. The last starlight in 2008, astrophysicist Fred Adams updated earlier work with Greg Laughlin on the 5 ages of the universe, calculating how long existing stars can shine. Published in the book The 5 Ages of the Universe, their models show that the longest-lived red dwarfs can burn for up to 10 trillion years. Compared to the 13.8 billion year age of the universe, that is staggering. A single small star could outlive the current universe almost 1,000 times over. But after about 10 to 14 trillion years, even these dim red embers exhaust their fuel. The cosmos passes into the degenerate era, a universe of white dwarfs, brown dwarfs, neutron stars and black holes. No new nuclear fires spark to life. The night isn't just dark, it is permanently darkening. We have never observed a red dwarf reach the end of its life. We have also never found a law of physics that lets a dead star reignite itself. Number 5. Black dwarfs and frozen remnants in 2013, theoretical physicist Matt Kaplan, later writing in monthly notices of the Royal Astronomical Society, examined the fate of white dwarfs over absurd timescales. As they cool, they're expected to crystallize into solid spheres of carbon and oxygen. Black dwarfs, radiating almost no light. Picture our sun as a shrunken Earth-sized diamond, black and cold, orbiting a dead galactic core. Not for millions of years. Not for billions. But for a time so long that the word year stops making sense. Up to 10 to the power of 15 years and beyond. On those scales, random quantum events might occasionally trigger what Kaplan called black dwarf supernovae, but each one is a lonely, final gasp in an otherwise silent universe. Most remnants simply fade toward absolute zero. No black dwarf has ever been seen. The universe is too young for them to exist yet. But we also have no competing theory for what white dwarfs become over that much time. Number 4. Galactic erasure in 1998. Observations of distant Type Ia supernovae by the Supernova Cosmology Project and the High Z Supernova Search Team, led by Saul Perlmutter, Brian Schmidt and Adam Rees, revealed that cosmic expansion is accelerating. This discovery, later awarded the 2011 Nobel Prize in Physics, forced cosmologists to accept something called dark energy. On the scale of a galaxy, gravity can still hold matter together. But between galaxy clusters, dark energy wins. Over tens of billions, then hundreds of billions of years, it pushes everything apart faster and faster. Eventually, only the most tightly bound structures remain. The Milky Way and Andromeda will have merged long before, forming one island universe. Beyond its outer halo, all other galaxies slip beyond our cosmic horizon. From inside, it will look like the universe has erased everything else. We have not measured dark energy changing with time. We have also not proved it will remain constant forever. Number 3. Black holes rule the dark. In 1974, Stephen Hawking published a paper in Nature showing that black holes are not perfectly black. Quantum effects near the event horizon should make them slowly emit radiation and lose mass, a process now known as Hawking radiation. Take a stellar mass black hole, 10 times the mass of the Sun. According to Hawking's formula, it would take around 10 to the 67 years to evaporate. A supermassive black hole with a billion solar masses could take 10 to the 100 years or more. These are numbers with more zeros than there are atoms in the observable universe. In this era, almost everything that remains, dead stars, stray planets, the wreckage of galaxies, is slowly eaten by black holes. Then, across 100 Google years, those black holes themselves leak away into a thin fog of low-energy radiation. We have not yet detected Hawking radiation directly. We have also not found a consistent theory of gravity that makes it go away. Number 2. Heat death, or something worse. The idea of heat death dates back to the 19th century, from the work of Rudolf Clausius and Lord Kelvin on thermodynamics. In modern cosmology, this translates into a universe that expands forever while its energy spreads thinner and thinner, approaching a uniform lukewarm nothing. Imagine all matter dissolved into a sparse gas of photons and elementary particles at a temperature barely above absolute zero. No gradients, no free energy, no processes that can do work. Time loses any era we would recognize because nothing macroscopic is left to change. This is the standard prediction if dark energy stays constant, an eternal, empty expansion. But some models of dark energy, like phantom energy with an equation of state less than -1, allow something even more violent. A big rip, where, trillions of years from now, expansion becomes so extreme that it tears galaxies, stars, planets, even atoms apart. We have not confirmed heat death. We have also not ruled out a rip that destroys every bond in nature. Number 1. Vacuum decay. The Trapdoor Under Reality. In 2014, a paper by Joseph Liken of Fermilab and Alessandro Strumia, presented at CERN and later discussed in Physics Letters B, used measurements of the Higgs boson mass from the Large Hadron Collider to evaluate the stability of our vacuum. Their conclusion was unnerving. With the Higgs at about 125 giga-electronvolts, our universe may be only metastable. On human scales, empty space seems simple. But in quantum field theory, the vacuum is more like a landscape of possible energy states. Metastable means we might be sitting in a long-lived, but not truly lowest energy, valley. If that is true, then, at some unimaginable time, or at any moment, a tiny region of space could tunnel into a lower energy state. A true vacuum bubble would form and expand at nearly the speed of light, rewriting the laws of physics inside it. Every particle, every atom, every black hole, every structure, annihilated or transformed with no warning and no possible defense. We have not seen any sign of vacuum decay. We have also not proved that our vacuum is absolutely stable. And now that you know this, the quiet darkness between the stars is no longer just empty to you. It is a story still being written, with an ending only partly revealed. If the universe might end in a whisper of cold photons, or in a single catastrophic flicker of the vacuum, what does final moment even mean? This is only one map of cosmic endings. The next episode explores another forbidden frontier. What really happens to information inside black holes, and why that paradox may decide the universe's fate. If you want to be there when we open that case file, the subscribe button is waiting, just below the screen you're watching now.